Steffens. I'll be moderating today's webinar, CMAC Design Optimizing Underground Detention. I'm joined today by three terrific engineers, Rosa Santillan, who's a project manager for Opti based in Atlanta. She's been designing these projects for some time now, and so she's also been the shining star of these design series webinars and has done a couple already, so she should be a familiar face to you if you've been following us. Also joining us is Dayton Marchese, who's over our strategic partnerships across Opti, across the nation. But he's been with Opti for several years and has gone through all those stages, being a project manager, a designer, and now managing these partnerships. He worked directly on the Aiken, South Carolina project that's going to be spotlighted and highlighted today with our wonderful partners over at McCormick Taylor, who's joining us today, Jason Hetrick, who is the Assistant Director of Water Resources for McCormick Taylor, based in Columbia, South Carolina. So thank you all for being here today. Thank you to our speakers and our experts who are going to be sharing with us. I want to remind you all that this is a series, and we do have the previous videos are available on demand. If you go to our website, just optirtc.com/resources. If you scroll down, you'll see the webinar series there, where we've gone through a feasibility assessments, a solution design, and then last month we went into a deep dive on how to calculate impervious acre credits in Maryland. Well, we're going to go back to basics with underground detention, and today it's showing you just what Opti can do to optimize those programs for you. Without further ado, I'm going to pass this off to Rosa, who's going to take us through these designs. Thank you very much.
Great. Thank you for that great introduction, Jennifer. I'm super excited to be here with our guest speaker as well from Taylor McCormick. Again, I'm Rosa, PM here. It's always a pleasure to talk to the audience because afterwards we have some great conversations around these topics. And something that's come up is underground detention systems. So today we're here to talk about that. And again, as Jennifer said, if you have any questions, if you have any interesting facts or any experience working with Opti, feel free to raise your hand or add something in the Q&A or the chat, and happy to stop and continue the chit chat. So just talking about stormwater management challenges, right? We're all here with, we've had that experience of scratching our heads of how do we address these challenges that are ever growing? So here we have a list, we have limited resources, aging infrastructure, which has been a major topic recently, public and staff safety, the list goes on and on and on, especially as new technology, new emerging design approach come into the light. This list will continue to grow. So today we're talking about exactly how is it that we can implement CMAC into our new designs. And as a quick recap, again, going back to our first two webinars where we talk about the basics, the 101 of what is CMAC, and then of course going into more in-depth discussions about simulations, and then Maryland. Just as a quick recap, CMAC is comprised of two main components. We have Opti partners with third-party infrastructure suppliers for hardware, and then we merge that in with our IoT services, which is software-based. And again, I won't go into a lot of detail. If you're very interested in that, we have those two webinars where you can learn a lot more about that if you haven't already seen them. But essentially, we're just bringing in the known with the innovation. And we'll be talking specifically about underground detention systems today. I think previous discussions have all been about surface ponds and above ground type of infrastructure, as you see here, a little pretty duck there, reservoirs, wetlands. So today we just want to spotlight underground detention system, which have been around for some time, but again, as technology grows, how can we adapt to those changing design criteria? And of course, we can't move on without really acknowledging what those challenges are with the passive or traditional approaches. And I think, so I come from a background in civil site design, and a big part of this was, of course, limited resources and budget, right? That's always super important. Adapting to a changing environment, just talked about that. And once that punch list is done deal, then there's also operation and maintenance that happens. But during the process, you also have other things like site constraints, and that could be buildable area. And I'm sure, like I'm personally here in Atlanta, where we're running out of room for surface ponds, right? Which is another reason why we're utilizing underground detention systems, whether that's chamber systems like you see here on the left here, or cast in place vaults, or already precast structures that you'll see in one of our case studies. Whatever the deal is, you do have that commonality of site constraints. Stream buffers, I dealt with a lot of those as well, where you might have plenty of space, but then you have those 75-foot, 50-foot buffers that you just cannot disturb. Erosion control is another big deal. Let's not get into cost and disruptions, right? That's another big topic. And then how do you know that your system is actually functioning the way that it was designed to function? You put it in the ground, and we all trust in our abilities to know that this system is going to be functioning the way it was designed for the life and safety of those around the system. So CMAC can certainly help with all these areas and potentially even more. Here's a quick graphic. Let's see. Okay, there we go. This is a quick graphic. You've probably seen another iteration of this where it was a surface pond, but again, we're talking underground here. So this is same type of hardware that you have seen before. We can implement it in the underground detention system where you have a pressure transducer that measures the water level. You also have your valve here. It's, of course, a very animated graphical representation of this. So you have your valve that's controlling open, close. This could be butterfly valve or slide gates. You have your actuator. And all of this is hardwired into our control panel that we do have solar inline power. And then the control panel is communicating with the OptiCloud via cellular network in real time, as well as receiving information from forecast. With all of that, the user can use a web-based dashboard to see real-time information as to how the system is functioning. So again, going back to how is the system performing? And another beautiful thing about this system with CMAC is that it's fully adjustable. So we do have an optimization period, but then for the life of the project, the system can be adjusted again to that changing environment, whether it's above ground, underground, it works exactly the same way. See? This is a good example of areas where we typically see underground detention systems. This is directly from one of our ongoing projects where you see that there is a court, just a sports court. And underneath here, we have a series of chamber systems. This is an ADS StormTech 3500, I'm sorry. And this can be connected, as with any other system, to your outlet control structure. And that is where we integrate CMAC. So the next slide, you'll see a very, very high level annotation and markups, equivalent to maybe about a 10% design drawing set, where we're still trying to figure out where everything is going. We're still trying to figure out pipe sizing, where the outlet control structure will be placed, the sizing, all of that good stuff. So we work with the engineer of record to identify the best possible area for the control panel. Remember that that's part of the hardware. Where are the conduits coming and going from? In this case, this project is a line power system, so we will be connecting to a nearby power utility cable there. So we work with engineer of record just to lay everything out. And then as the project moves from 10%, 30%, 90%, up to 100% design drawings, it's fully customizable in terms of having certified hardware, but in terms of where the location of this hardware is best suited for the site. In this particular instance, talking about constraint, we did find that the property line is about here. You can see my cursor there. And then we have a building that is pretty close to that property line. And then we have a wall that's going right up against there. Talk about site constraints, right? Everything will be housed completely in the underground outlet control structure. And then the only thing you'll see is a control panel. And so again, we work with the design as it changes, as it shifts. If there's a change of scope, then we are part of that process the entire way. So that was a chamber system. But if you can see here, again, this is a very graphical representation of where the Opti control panel and the valve would be installed. Here, you can't really see the leader there, but this is a 4-inch orifice. In the valve itself, we match it to whatever the orifice size is for the project. This is a volt system that can be used either for irrigation purposes, for attenuating and minimizing discharge, in a variety of other reasons that maybe we want to contain rather than infiltrate. And we'll be talking about that more so when I hand it over to Dayton. He talks about the case study. But yeah, so you can house the entire system inside of the volt itself. And you'll never even know it's there. The conduits will come out and then they will connect to the control panel that many times it is within the mechanical room where you house your water meters and whatnot. So that can be housed, the actual control panel can be housed inside of the mechanical room. No issues at all. We'll just find the placement for the antenna to make sure that we are properly sending and receiving signals from the antenna itself. And then here, I really like this representation here because you can see that everything is there. You've got your valve, your stem, your actuator, and then it's just sending the signal to the cloud while on the surface level, you have all this beautiful usable space that we're starting to see. And a lot of municipalities actually give you credit for using green infrastructure and maybe pervious and impervious pavers that infiltrate into your system depending on your design. But the Opti system itself is made out of those components: the valve, the stem, the actuator. The flow sensor will probably be housed on this side of the weir wall. And then from there, everything is connected to the control panel and conduit can run wherever you need that to be. Opti also, as you may have seen in previous webinars, we also support our partners and customers with a set of design drawings. We're able to provide these in PDFs or CAD file as well so that you can customize your outlet control structure. And we'll work with you to verify that the setting is correct or that that you're using the right dimensions, that we have the information needed to integrate the control settings, such as any elevations, if you have any weir walls, overflow weirs, any constraints within the outlet control structure. We'll work through all of that. And then this is one of my favorite parts. I'm not sure if anybody here in attendance, if you were at CESWA just last week, but I think this is a national conversation that is happening around grants. So there is a lot of effort to provide grants at the municipality level, whether that's city, county, state. There's a lot of grants out there to be used. And during CESWA, we talked about a lot of having multiple benefits, right? Stacking your benefits and having the best chance of getting those funds allocated for your project. And Opti can help you with that. Opti can be used for a multitude of benefits all at once. And you'll see in this case study that we'll see here shortly, we talked about flood mitigation, hydromodification to reduce some of those erosive flows. That was such a big deal for that project. Water quality. You can also have some other projects that might also integrate water conservation, and the list goes on. So as we're moving into this era of more focus on stormwater management and having all of these wonderful grants available for project use, let's brainstorm and see how Opti can help you hit as many of those stacked benefits as possible when applying for grants. Here. And then here's a flow chart. Again, you may have seen this as well, but just want to reiterate basically the life cycle of how we get where we are. We identify the challenges, again, those stacked benefits. What are the challenges? And for every challenge, there's an objective. And then we can also identify some of the KPIs that go with that. We select the behavior on the control settings that are the inner workings of the system, the actual software. We also establish those key parameters. How do you want the system to function? And Dayton will go more into detail on that for this particular case study. But do you want the system to hold the stormwater for a certain amount of time for, 4 hours, 5 hours, 24 hours, whatever that is? and then slowly release for water quality purposes. Whatever that is, we identify those KPIs during this stage, and then we go into H&H model and simulation, which Kenneth Yu from Opti, our hydroinformatic engineer, we're into a lot of detail on that in seminar number 2. So if you're interested in learning more about these simulations, I refer you over to that seminar, and he goes into really, really good detail. And if you have any questions, please feel free to reach out and see how we can partner with any models that you may already have in your design. And then finally, top priority here is safety, right? How do we make sure that our systems are safe, that they are reliable? And of course, redundancy, right? That's part of every engineering project. We make sure that the civil design is there. So we do not necessarily replace, but rather enhance passive overflow that's been designed by the engineer record during a passive system. We simply enhance the design. We also do downstream condition assessment, and we can do that during the feasibility assessment. We provide mechanical and cloud-based security as well, and we can go into more detail that in future seminars. But we just want to make sure that we are providing our partners, our customers, and the end user with that peace of mind that we do have a set of security, reliability, and redundancy practices in place. And then, of course, we talk about this every time, but we are growing as, you know, more and more projects are coming, but we're already in over 300 different deployments. We are backed up by a variety of different regulatory approvals. And again, going based on those grants that we talked about during CESWA and other national conferences, we are part of that conversation. We are at the table learning more about how we can support these efforts as a whole. So we're currently in 37 states and growing. So love to hear about where your projects are. And yeah, let's talk. Partnering for success is our also top tier priority here, right? We partner with you so that you can provide your local expertise. You know your state, you know your design. Let's talk, let's brainstorm, let's share models and design. And we also provide you with a lot of support from start to finish, and even through O&M management, operations and management with our Opti technology. And then together we can just work towards that common goal of providing clean, water resilient communities with that peace of mind. And with that, I'm going to go ahead and pass it over to Dayton, where he can talk more about the Sand River Stormwater Project that has been a wonderful success. And I'm sure there's a lot of you here in attendance that might have had some part to play. So thank you, everyone. I'll go ahead and pass it over to Jason and Dayton for this.
Great. Thanks, Rosa. Appreciate it. Jason, good to see you. Welcome.
Good to see you again, Dayton. It's been a while.
Yeah. Appreciate you joining us. I'm excited to talk about this project. Excited to talk about it with you. This is one of my favorite Opti projects that I've ever done. I've done a good number of projects over the last 7 years or so. Definitely one of my favorites for a couple of reasons. One, you put together a great project team. They're very smart, capable, enthusiastic. 2, we have some slightly complex control logic, which you'll remember in the design process made this a really fun project to do. And 3, it just provides a ton of value for the community. And you're close to this, you're local, you've seen a lot of this. So I'm excited to jump into it. We'll share with the community a little bit about the project, how we implemented it, and have a good conversation.
Great.
So I wanted to start out just talking about the city of Aiken. So city of Aiken, mid-sized city of just over 30,000 people, right across from Augusta, founded in the early 1800s. And one thing about Aiken, and Jason, I think you told me a little bit about this when I was there visiting, it really started as a summer community for people in the Northeast. So people in New York would come down, they would spend their time, they would ride their horses, big equestrian community. Early on, didn't have a big downtown, but then it started to develop a big downtown. You can see it right here. The equestrian community, still today, they use this amenity, Hitchcock Woods, significantly. They spend their time hiking, riding horses in there, and it has running through it, which you can see, the Sand River. So Hitchcock Woods, the Sand River. Here's a little sneak peek at where the project we're going to talk about today is. It's right at the headwaters of the Sand River, right where basically the urban downtown area meets up with Hitchcock Woods. Anything else you want to add about the city?
No, you nailed it on the head. Aiken was born as a winter playground for the New York City elite. They would bring their horses and friends down for the winter and go do fox hunts and equestrian activities. And also, it was a major hub in the railroad system from Savannah and Charleston up to the inland area. So kind of a dual birth to Aiken, the railroad and the equestrian community, and which Hitchcock Woods is it's a huge gem of the city of Aiken, and was kind of the impetus on this project on preserving the jewel that's in their backyard.
So let's talk a little bit about that impetus real quick. So the Sand River, which used to be, as I understand it, a small, narrow river that someone could hop from one side to the next. Is that right?
Correct. Yeah. So the gentleman there in the middle, his name's Bennett. He grew up in the woods, and there he manages the woods. And he remembers as a child, not that long ago, that you could just hop over the Sand River. It was a little babbling brook, creek. One of the some of the older members of the woods would just skip over it, and then the last 30, dating myself here, probably the last 50 years, the acceleration of erosion has just been exponential due to the increased impervious area within the 1,200 acre watershed.
I will say some of the impervious area and some of the pervious area upstream is actually pretty exciting, Nick. And they've got their nice downtown walkway, their sort of outdoor shops and restaurants. It's a very fun place to be, but I know it carries with it some consequences.
Correct, and actually, it could be probably the runoff would be 1,000 times worse if it wasn't for Aiken's Parkway system. They have large, broad boulevards with treed and grass medians, a lot of tree canopy in the watershed, which um, does help. But as you can see from these pictures, it doesn't do enough in mitigating the runoff from such an urban area.
But Aiken and the community there, they decided to do something about this, right? So they formed the Sand River Stormwater Task Force, which you were a key part of.
Correct. Just prior to our involvement, Mayor Osmond in 2016 formed the City of Aiken Stormwater Task Force, which was comprised of members from the Hitchcock Woods Foundation, elected city officials, city DPW folks, and then also residents of the community. Aiken is special in the fact that it sits adjacent to the Savannah River nuclear site, so it has a host or a good clientele of engineers and scientists that call Aiken home, and those folks were part of this task force. So we were really able to have really constructive scientific dialogues in developing the ultimate strategy to address the erosion within the river.
And that was the big focus, right? It's what can be done to address that erosion. And when McCormick Taylor was deeply involved in the technical side, right? You did the modeling for this, you broke down the city into these different sub-watersheds.
Correct. Yeah. So the 1,200 acres that drain to the headwaters of Sand River is basically arrives at the Sand River in two large sub basins. You can see here, one to the west side of the city, that is the historic downtown area that gets to the Sand River very quickly. And then to the east side of the city, there is a much larger, broader drainage area that consists of several sub basins that makes its way there. And we did traditional hydrology for the basins using TR20 to determine what the runoff was coming into the area, and also what it would be if Aiken wasn't there, if it was just the pine forest and the sand hills that 200 years ago or 250 years ago before Aiken became Aiken.
And so you had a goal, or the team really had a goal of restoring this pre-development hydrology and managing the 10-year storm. So you did the modeling, you identified the drainage areas, and you identified a target storage volume that would be needed in order to mitigate that 10-year storm.
Correct. So we looked at various storm events, trying to figure out what would be the most practical, plausible, and cost appropriate management storm to look at. As you can see here, we can the 1 year, if we're going to manage the 1 year storm back to pre-existing woods condition. So wiping all the impervious area out, and what would be the runoff if it was the forest. It was still a sizable amount, 26 acre feet. When we looked all the way up to the 25 and 50 year storm, which didn't make this chart, And what we ended up going with was the 10-year event. One, because that's the common, metric for new development in Aiken in South Carolina, managing the 10-year back to the pre-development conditions. And also gave us a volume that we felt that was plausible to achieve, and that we could meet that goal, and then look beyond that in the future, for future projects.
It's not easy to find 58 acre feet of storage sitting in an urban area of Aiken, is it?
Yeah, so that quickly proved to be a challenge. Like I said, Aiken is a historic city, very built out, not a lot of open space, publicly owned open space available. And if it was heavily treed. Aiken is a tree city and they hold their trees quite dearly. So even if it was a publicly owned lot, most of those lots were excluded due to the grand, live oaks and other very grand trees growing there. So that's when we started to look for alternatives.
But you did, so the team did identify 20
Yep.
projects approximately, right, that could meet the 58 acre feet, not
Yep.
inexpensive.
Yeah, so you can see on this map, we started out with probably 50 conceptual locations, and through ground truthing and doing some preliminary design, we quickly pared that down to 20 locations that would get us to the 58 acre feet, all on publicly owned right of way, whether it be school locations or roadway right of way, public parks, that sort of thing. And it was, they said it got very expensive, not only for the construction, but also for the long-term maintenance that the city would have to endure, maintaining 20 stormwater facilities scattered throughout its jurisdiction.
Yeah, that's something that's not always considered when looking at some of these watershed plans. So, it's good you all included it. But one of these projects, or I guess two of these projects, they jumped out as being the largest right here at the headwaters.
Yeah, so at first, common stormwater, I guess metrics today is, we don't look at end of pipe treatment options. We try to put the treatment options throughout the watershed, and which is, as you can see here with the 20 some projects, that was our first approach. But then when we started looking at the cost, the maintenance, and how much the time frame needed to actually implement and build these projects, we quickly realized that we needed to look at an end of pipe treatment system where we can come in and get a very quick return on our investment and make a sizable dent in that quantity management that we were projecting to do. So which brought Stormwater Management 6 and 6A to the forefront, which is located right at the terminus of the storm drain system.
And we have a picture of the design of that, and maybe you can walk us through this in a minute. And this isn't exactly what what I'll call a more traditional passive design. So this was the design that you did that included real-time controls, which is what we're going to talk about. But maybe you can just talk us through sort of the flows, where water's coming from and going in the system.
Sure. So as you can see here, we were confined to working within city-owned parcels. In fact, we had to work with the Hitchcock Woods to donate some land as well, but we were very confined footprint-wise, in room to do something. So that quickly rolled out doing a conventional above ground stormwater detention pond. You can see from the contours here, it's a very steep site with a lot of terrain. BMP 6A is located it's located in the old riverbed. So there was a canyon-esque feature there. So that really limited us in what we were able to do stormwater management wise, which guided us to underground management. But as you can see here, BMP 6 is the upstream, or the first BMP that receives runoff. There's two inflow points, one coming down from the top of the screen into the facility through the first inflow pipe. And then at the bottom right-hand corner of the screen, where it says 48-inch storm drain pipe, there's another inflow point into BMP 6. And that captures those two nodes of that watershed that was on the previous screen, and routes it into that vault. That vault, BMP 6 by itself stores 17 acre feet of runoff, which was great, but wasn't enough. So we looked at BMP 6A, which is located downstream of 6, to get another 7 acre feet of storage in that vault. And they're connected hydraulically through a rather large orifice, a 36-inch by 36-inch orifice at the BMP 6 end, so that the water routes through BMP 6 and the 6A, and then the secondary outfall from 6A then goes into the Sand River. Any overflow from BMP6 when BMP6 is full spills over through an emergency spillway, so to speak, a very large pipe that then ties back into that existing 84-inch storm drain system pipe that runs basically from northeast to southwest through the picture there.
And despite being 25 acre feet, this site is actually, quote, undersized. You would have designed it larger had there been more space available, or you weren't tied to site constraints due to elevation or property ownership.
Yep. So we were constrained by property footprint, and also we've utilized this was a storm trap double vault, which at the time was the largest concrete vault system on the market, a 15-foot internal clearance. We could not squeeze any more storage out of these sites. And as you can tell that on the previous slide, the 1-year storm management was 26 acre feet. So by itself, without Opti, we would be passively managing only the 1-year storm event, and as a detention facility, not as an infiltration facility, which Opti allowed us to do.
So those were some of the site constraints. Given the site constraints, space, property ownership, elevation, you and the team were looking at optimizing it. So that's when you engaged Opti to look at a continuous monitoring and adaptive control, or CMAC, or real-time control solution. And from a hardware perspective, this was relatively straightforward. You designed 36 by 36 inch slide gates to go on the outlets of both BMP6 and BMP6A.
Correct. And the question might be is, well, why did we pick 36-inch by 36-inch? And one of the benefits of the Opti system is that the slide gate can be incrementally adjusted from basically a ½ inch up to full open. So that allowed us to have maximum control of discharge out of one vault into another vault. We were confined to 36 inches because that was the maximum opening storm trap would comfortably allow in their precast vault panels due to rebar and reinforcing issue. And also a slide gate any larger than that would be quite intense to install and maintain, and would require quite a motor system to raise and lower. So we went with the 36-inch vault opening just to make sure we could maximize the dynamic flow coming out of the systems from practically nothing to full blast.
Yeah, that's the great thing about this, is we can, for really large storm events, we can open these gates at the start of the storm, let that initial flow go through, and then close them off so we can capture the peak and then hold that water back and infiltrate it. So to your point, it's dynamic. We talked through the civil design considerations. So you were the lead civil design. We talked through the existing conditions, drainage area, storage capacity, the 25 acre feet, controllable volume, so it's controlling the whole thing, cellular connectivity, power. These are both line power systems. So you designed a power drop on site. And then of course that overflow you called out. And these are just some of the considerations that we go through for these design projects to make sure it's both meeting the needs and also being safe and covering everyone's bases. So I know you mentioned the elevation challenges. So we put this on here to give a little bit more scale to those elevation challenges. So this is BMP6, which is upstream, which flows down, enters that pipe, and then goes into BMP6, which is downstream.
Yeah, there's approximately a 40-foot elevation difference between the bottom of BMP6 and BMP6A. There's huge topography change over the site, which created a challenge in conveying the flow from one vault to the other. And as Dayton will get into shortly, is also how to sync the two Opti systems together so that they're integrated in parallel or in series.
And that's the takeaway. We can't operate this as just one hydraulically connected system. We couldn't just put an outlet gate on BMP6A and hold water back and utilize the storage volumes in both systems. We had to put 2 control gates on there and then coordinate them together. So that took some simulation. So first we identified the stormwater challenges together. We chose the behaviors. So we were trying to target reducing peak discharge and maximizing infiltration. Those are the 2 primary hydraulic goals of the system. We then configure the parameters and then we simulate it. I remember this, this is generally what we came up with. This is an illustrative example of how the system was going to operate. We broke it down into 3 components. So how is the system going to operate in small storms, meaning less than the storage capacity of BMP6A. And what we've said is this system is going to pass flow through BMP6 into the downstream BMP6A, which is then going to hold it throughout the storm and then infiltrate. And can you remind me, why did we pick BMP6A as the vault that was going to be used primarily for these more frequent small storm events?
So BMP6A sits right on a lovely layer of prehistoric beach sand. So the infiltration rates were around 17 inches per hour. It was just had a very high infiltration rate. So we wanted to maximize the amount of water being pushed into 6A, capture it so it would infiltrate. It was infiltrating a lot quicker than 6 was, which was sitting on a kaolin clay layer. To access the sand, subsurface sand layer where BMP6 was located, we actually installed 25-foot deep stone chimneys that were about 4 to 5 foot in diameter throughout the footprint of the vault. So while 6 infiltrates, it infiltrates at a much slower rate than 6A. So 6 is the shock absorber in the system, so to speak. It collects all of the runoff and then meters it out to 6A as 6A infiltrates.
So that's what we're doing for the small storms. And then the medium storms is similar. So these are storms that will fill up 6A. So first we let 6A fill up, and then when it's full, then the gates at 6 close, and then we start to fill up BMP6. At the ending of the storm, these are both relatively full, and then they hold water and infiltrate. And then finally, we broke it out into large storms. So these are storm events that are greater than the combined volume of both vaults. And for these, we want the gates of both systems to be open at the start of the storm to pass that slower flow before closing off and then retaining water. And then at the end of the storm, both are full before they infiltrate.
And that was a really important aspect of the design, because the receiving stream is a sand-based channel and it erodes very easily. So to minimize the erosion, we really wanted to capture that peak runoff event coming from the storm event, the most destructive amount of erosion. So we were willing to let that, perhaps that water quality first flush bypass through the system, because that was going to do the least amount of damage to the sand river, the sand channel, and then shut the gates so that we can capture the most destructive part of the storm, so to speak, and mitigate the erosion downstream.
And there is a little bit of depth inside both of these vaults between the invert of the gate and the vault bottom. So there's a little bit of capture there, but you're right, we wanted to push that early volume through. So we did some configuration. Here's a list of some of the parameters. I think the biggest takeaway for this, and what's very exciting in my mind, is this represents a paradigm shift from the traditional engineering approach, which is model, maybe monitor, design, build, and walk away, to, well, now we can model, we can monitor, we can design it, we can build it, and then we can observe how it's performing and then make some adjustments to the control parameters. That's during the optimization phase. So after we, turn the system into automatic mode, we were watching it very regularly to see how it was performing to these storm events, whether it was getting more flow than expected or less flow than expected, or whether it needed to be more or less responsive to the weather forecast. And these were parameters that you and I and our teams are going back and forth on throughout the early phases of the project. And it's exciting because now we have it dialed in pretty well, but there's still opportunities to adjust it.
Yeah, one of the most challenging things of the Aiken topography is predicting the hydrology and the runoff through that watershed. Aiken has a very unique soil complexity. Some areas are sand, some are clay. Has a very disconnected drainage system. So there's been countless number of hydraulic models done on this watershed, and each one came out with a different result. So it's like, what do you base your design on? So using the Opti system, we're actually able to calibrate and base the design on real world results instead of a model that could potentially be quite wrong.
Right. And update it as we need to. If the upstream urban area changes or regulations changes or any other changing in frequency of rainfall patterns, those are things that can be incorporated in the control logic in the future as needed. So here's some of the simulation results. This is what you and I came to. You modeled the system. We added some opti control logic and saw that we were getting anywhere from a 2 to 3x increase in wet weather volume capture, which is the amount of stormwater kept out of the downstream system during that critical wet weather window. And we're also seeing a significant increase in infiltration because the system is now able to capture and fully infiltrate the more frequent small to medium storm events. We have some images. Some of these I think came from your team during the construction. I love showing these. It shows the scale of what you are working with on site. So that's BMP6, the upstream one. This is 6A, right? So we see the crane here for scale. I think we have a couple more to share. So this is another one for 6A. Let me look at these. We have the people on there, and then this is one of my favorite photos of it.
That's BMP6 right there. Makes the large tractor trailer look like a Matchbox car, and each vault piece could fit one per trailer on average. So we had over 1,200 tractor trailer deliveries to this site.
Yeah, this was Storm Trap. So they've got their vault system on there. It was very exciting. But yeah, the logistics of trying to get all of those truck pieces in there is almost a project in and of itself.
It's pretty tight.
Yeah. So we have some pictures of the control hardware. So this is a top view of the actuated gate. So the actuator gate assembly within the outlet control structure. There's a control panel. It has a cellular antenna on it, so it's reporting up to the Opti software platform. A rain gauge on site, power drop, and then a level sensor in the steering well. So here's some photos from the completed construction. What's the park used for now?
So it's a surprisingly, it's very well used. It's a passive park, has some pervious walking trails, pathways through it, native landscaping, a rain garden. People use it to, it provides a connection from downtown Aiken to the entrance to Hitchcock Woods. So there's a lot of pedestrian traffic walking from, grabbing lunch and then to go take a walk through the woods afterwards. So just general recreational activities, nothing structured.
So we have just a couple of dashboard shots we can take a look at so we can see how the system is operating. So this is from a storm event from last year. You can see in this third bucket, rainfall's coming in and ticking up. This is about a 1-inch storm event. Flow passes through the upstream BMP, so that's this top graph. And then it fills up the downstream one. We can see if we can get another look at this. Let's see, here we go. Yeah, so this is actually 2 back-to-back storm events. So first storm comes in about almost a 1-inch event. Water passes through BMP6, the upstream one fills up the downstream one, and then fully infiltrates. So in this interstorm period, the gate for the downstream BMP6A doesn't open at all, and it's infiltrating this volume. Then the second storm event comes in over 1 inch, starts to pass through the upstream BMP into the downstream BMP until the downstream BMP is full, at which case the gates for the upstream BMP close, and then the upstream BMP fills up. So this is the system working and coordinating together to say, let's try and pass flow into the downstream site as much as possible. Unless it's full, then use the upstream one. We have one more storm that we wanted to look at. This one's actually, so this one's fun. This is a storm event that happened last month. So we can see we're looking at the upstream volume over time, we're looking at the downstream volume over time, and we're looking at rainfall here. So we can see these are essentially 3 storm events that happen all right around. These first 2 are just over 1 inch, just under 1 inch, and then the other one is about 0.65 inches. And we can see that the downstream EMP is actually infiltrating volume from a past storm event before this first storm event comes in. And then the system clocks that there's not going to be enough capacity in both systems. So the downstream BMP releases water into the Sand River in advance of the storm during dry weather. System fills up, triggers at the upstream BMP to close, and then we're utilizing the volume from both sites. And then the other thing is these systems are full before this last storm event comes in. And we see the downstream BMP automatically opens in that dry period again to create some additional capacity. So we talked a little bit about the infiltration rates, and we looked at a couple of different storm events for both of these BMPs, and we thought this was a fun thing to share. So for BMP6, and I think this mirrors what you were mentioning earlier, Jason, BMP6 actually has good infiltration rates when it comes compared to any other, general stormwater project. Now that you put in those stone chimneys, it's getting anywhere from around 1/2 inch to maybe 2 inches per hour, a little bit more at higher elevations. And then BMP6A is around 2 to 3 inches per hour for most elevations, a little bit more when we get higher volumes in these systems. And is this about what you would expect post installation?
Yeah, I'm really happy with these sort of infiltration rates, especially when you're considering the amount of construction equipment that we're sitting on top of this material to create a gravel sub base, a crane sitting on it. The contractor tried their best to minimize compaction, but at the end of the day, it's really hard to prevent that. And so I think anytime when we have over an inch of infiltration rate in the stormwater industry, we're happy, especially when you get to 2 to 3 inches. So this really does make a huge impact in reducing the amount of runoff that's running into the Sand River every rain event.
And what's great is we're going to be able to track this over time also. So we can see if there's maintenance required or any other needs for the site.
Yeah, I mean, the biggest takeaway is that most average rain events that we get, we're able to capture 100% of that volume and infiltrate it. So that's removing that continuous erosion within the Sand River out. And really the only erosion that does occur moving forward is those, really more intense storms that happen every couple months instead of every other week. So it's making a huge, sizable difference.
Yeah, so we wanted to revisit this, given that the site is working, it's working very well, it's capturing more stormwater than originally expected. Does that mean that this watershed plan will then be updated, where maybe the least cost-effective projects might be reconsidered, since the city is able to meet their goals better with fewer facilities?
Yeah, 100%. At this time, the city has, there's really no need to move forward with any additional projects. The Opti control system is basically creating the same result, if not better, than if all these additional 20 projects were implemented. So we were able to basically solve tackle the problem with one project instead of 20, save the city at least $10 million, if not more, considering we're now in the post-COVID era where inflation and everything. So probably $15 to $20 million cost savings in reality by just implementing one CMAC control project.
So I think that brings me to the takeaway. So you said, offset the need to spend millions of dollars. And the thing is, the city still can go spend that money, but it might be on public amenities or additional parks or other facilities or benefits to the community, because they're able to get the increased stormwater performance from this project, protect their critical resources. And this is a little bit of a plug for the project team. This project won a number of awards listed here on the right hand side, and I don't even think this is a complete list. I think you've won some additional awards since
Yep.
I put this together.
Yeah, so this spring we won the South Carolina ACEC Palmetto Award. It was one of the top 6 projects in the state.
Yeah, that's great. We just want to give hats off to the rest of the project team. So Theo was the contractor on this. Storm Trap obviously played a big role. You've also recently published a paper on this project, so if people want to learn more of the technical details, we can link them to that.
Correct. Yep.
So I think with that, unless there's any final thoughts you wanted to add, Jason, it sounds like we have a few minutes for some questions.
No, let's get some questions.
Terrific. What a great project. I'm going to invite Rosa to join us again and open it up for questions. I did want to note that I do see some of our friends from Storm Track on the call and wanted to give them the opportunity to share anything or if they had anything to add from this project. Don't feel the need to if you don't want to, but I just wanted to put that invite out there. While we're waiting on that, I want... Oh,
I was just going to say, as you mentioned, Storm Trap, this project was a huge success just between the collaboration between Opti and Storm Trap and ourselves and the city of Aiken and Taylor Construction. During the design phase, there was a lot of back and forth and iterations with all three parties, and it's just, great example of teamwork.
absolutely. No, it shows, this need for these partnerships and working together for continued success. So we really appreciate all Storm Trap's done for that, as well as our other partners that Dayton mentioned. One question I have here is you said that the volume that was captured from the two BMPs or the one, that was split into two, 6 and 6A, was about 25 acre feet. And you needed a total of 58 acre feet. Can you explain how you were able to increase that 25 acre feet to meet that your total volume needs?
I think, and I'll just maybe start off with Dayton. You can jump in on how the Opti optimizes the performance of the system, but through be able to dynamically control the low flow orifice, so to speak. We're not designing the low flow orifice of this detention vault to meet just one storm event. So we're able to throttle it so that it can work dynamically to provide more management. Also by being able to allow that first, say, non-impactive storm flow to pass through the system and capture the peak flow. We're not able to do that in a traditional system. So that's some of the ways that we're able to increase performance to get towards our 58 acre feet.
Yeah, I mean, I think you hit the nail on the head. If we looked at the course of a typical year, we looked at the peak flow rates coming out of that system, and we looked at what's causing sediment transport and the frequency with which those events actually discharge from the site, we would see that the frequency is much lower because we're able to hold water back and infiltrate for those more frequent small to medium-sized storm events. So the only storm events that are discharging out of the system are the larger, less frequent ones.
I think the best testament was talking to Bennett, who managed the woods, and he goes, "It's really weird to be in the Sand River while it's raining and have no water in the river, and then 10 days later in a sunny day have a slow trickle moving through the creek when it's drawing down for the next rain event in a much less violent way."
Less violent for sure. What was the original volume of outflow or rate of outflow?
The original outflow was a 120-inch CMP pipe that during any typical rain event would be flowing at least half full, and during a thunderstorm would be full flowing as a fire hose just throttling into the creek.
Wow. No wonder we had those 30-foot cliffs. Fascinating. Well, here's another question. Who's in charge of monitoring the results after construction? Who's managing this in the long run?
So for the short-term duration, we're still partnering with the city of Aiken to monitor the results, to see how the performance is moving over the next 3 years, putting together the data into a report and everything. The city of Aiken has a stormwater manager that is plugged into the whole system and can view the dashboard, and they're tracking the data internally as well.
And Jennifer, I do want to add, just in general, we do have 2 sets of dashboards that we found very useful, especially for projects where education is a huge discussion around the project. So we do have administrative control dashboards, and then we have view only dashboards as well, in case, for a high profile project like this one, if the community ever wants to get involved as to what happened now, like how is this functioning, and the city of Aiken decides that they want to share this information, they can do a view only. And we've seen that happen throughout other projects as well, where education is a key to the community. So I think it's just something fun to add to that.
Fantastic. Yeah, these are cloud-based. This is a cloud-based system, so the dashboards are accessed just via website, a portal with logon, and so the city or the stormwater managers have access to that, as well as their consulting engineers where they see that to be necessary. Terrific. Any questions from the panel? Or anything else that you wanted to share?
We didn't bring up funding for this project, but Jason, the city was able to get a couple of different grants to us. I mean, this whole project cost a little over $15 million, and they were able to fund it.
Yeah, so the project itself, which included the park on top and roadway reconstruction, a lot more than just the stormwater aspect of the project, was about $15.5 million. We were able to get South Carolina Department of Health and Environmental Control EPA 319 grant to fund the Opti system. And that also included 3 years of operational, membership, operational fees and things like that. So that paid for pretty much everything Opti related through the grant funding. And then we received some other grants here and there to help go into the pot, so to speak, and then a state revolving low interest water quality loan to cover about $6.5 million. So the city really pulled from various resources. Their hospitality tax paid for or covered the money needed to construct the park. Their stormwater fee covered the remainder of the underground stuff. I think the proudest thing is at the end of the day, we were able to build this project $15.5 million without any increase in the city's utility fee that it charges its property owners or any sort of tax increase. So we were able to really bring multiple pots of money, so to speak, and grant opportunities to the table. Using the new technology is always really appealing to grant agencies.
Speaking of that, was there any specific questions from the regulatory authorities when you said, hey, I'm going to be using real-time controls to slow these flows down?
I think they were highly skeptical and very inquisitive, which I think helped us be able to get the grant because we said, well, give us the money and we'll prove it to you. But we were able to direct them to the work you guys have been doing up in Albany and in the Chesapeake Bay watershed in Florida, just so that it's it's proven technology and there's many state agencies that are embracing it. So definitely a lot of curiosity about the project and the technology, but I think everybody's been very, very pleased with the results.
I look forward to you being able to deliver that report that shows them how it's been performing.
Yes, I have to get started on that.
Well, what a fun project with great results. I'm really excited that you were able to join us today, Jason. So thank you for that. Thank you, Dayton and Rosa. And thank you all who joined us in attendance. If you have any further questions, please feel free to reach out to us. You see the email addresses that are up there. And of course, you can always reach out to us online. We will be following up with a